Mm-hmm. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, all right. Let's see if we can. Okay, okay, okay. Okay. Let's take a look. Let's take a look. Calculus. Okay. All right, folks. We will get started pretty soon. So this is Math 1014. Homework number 1. Looks like it's just 7 quick problems. Shouldn't be too bad. Let's take a look. Right, okay. Calculus problems. First off, any particular problems? So, number 1. Okay. Let's see. Okay. Let's just go ahead and get started with the problems. So let's take a look. The first problem asks about some sort of Lorenz curve. So number 1 is this Lorenz curve. And the idea behind this problem is that you have some kind of curve that exists typically below the y is equal to x curve. So if y is equal to x is the ideal income distribution curve from 1 to 1, a lot of the times in other countries you have stuff that kind of looks like something like that. Something like that. And what this means is basically saying that if this is A and this is B, let's call that maybe A out of 100 and B out of 100. This is basically saying, what is it? A%. So the A% of poorest households receive B% of the money. So if this value over here is like 50% of the people of the houses get, I don't know, maybe like 10% of the income, that's like saying that things are probably not so well in whatever economy you've got set up. There's a lot of inequality. And the idea behind this problem is that, okay, so this is the curve itself, and the curve doesn't quite say, it's like you sort of want a holistic measure of how good or bad this curve is. And the idea that they came up with was basically to compare this to y is equal to x and just take the difference between them. And that difference can be obtained through, you guessed it, integration. And the idea behind this problem is that, so I guess we'll call it the GI for Gini index, is just equal to the integral from 0 to 1 of y is equal to x minus whatever your actual Lorenz curve is. So when, for part 1, they ask you kind of to do a qualitative interpretation of seeing that the point, I don't know, some particular point 0.5 and 0.125 is on some, is on the Lorenz curve. And to do that, you just have to, I mean, it's just asking you for a qualitative interpretation about what that income distribution means. And qualitatively, it's not so nice, right? It's saying 50% of the incomes have something like 12.5%. So just interpret that as you will, right? Just look back at the definition of the Lorenz curve and interpret that accordingly. But that's no calculus is involved yet. Part B is where the real calculus starts, and that's using the integration right here. It asks you to compute the Gini indexes of the countries A and B, which just means that for country A, LA of x is equal to x cubed. You just go ahead and plug that in there and integrate that difference. And for country B, it's kind of weird. It's sine of, what is this, pi over 2x? Minus pi over 2x cosine? Well, same idea. Just plug this entire thing into L of x and integrate it. And this one is slightly worse because there's just one kind of nasty term here where, okay, x is easy to integrate, sine of pi over 2x is easy, but pi over 2x cosine pi over 2x, this is going to require a tiny bit of integration by parts. I recommend using u is equal to x and v is equal to cosine pi over 2x. I guess this is dv. So do your integration by parts, and this should work out quite nicely. Any questions so far? Okie dokie. So part C just asks you to say, well, okay, look at your results from part B and just tell us which one has more income inequality. Basically just take your results from the integral and just see which one has the higher value, the higher area. And that's your measure of income inequality. Okay, so far so good. Now we're talking about the average value of continuous function f on some closed interval. So if you have f of average is equal to 1 over b minus a, integral from a to b, f of x dx. So in high school, you probably learned that the average of a collection of numbers is, sure, okay, the whatever average. So the question is asking you to say, given that f and g are both continuous on a comma b, on this interval of interest, and you know that f of x is less than or equal to g of x for every value inside the interval, we're going to use the comparison property of definite integrals to show that we want to show, WTS means want to show, f average is less than or equal to g average. And this should make perfectly intuitive sense, right? This is basically saying, okay, you have some function f, and you have some function g that's always greater than or equal to f. So if this is g of x and this is f of x, it's pretty clear that the area under the curve for any intervals a to b, well, it's pretty clear that the area under curve of g of x is greater than f of x. Another way to say that is the integral of g of x is greater than the integral of f of x, right? Because g of x itself is greater than f of x, of course the integrals must also have the same relationship. And then you just divide this by b minus a, and that's essentially the idea behind that problem. Yeah? Maybe I was saying too much. Anyways. The idea here is the crux of the problem comes down to showing that f of x is less than or equal to g of x, which is a perfectly intuitive idea. You just have to cite some comparison property to make that idea rigorous. So, okay. So far, so good. Now, the idea behind the next problem is that, let's say that f, the minimum value of f, is equal to little m, and the maximum value of f is equal to big M. And it's basically asking you to show what I think is a very reasonable visual intuition. But the idea here, if maybe f looks something like, let's say this is A and this is B, it's basically asking you to show that, excuse me. So if this is f, okay, if this is little m and this is big M, this is basically saying the area under the little m constant function is less than the area under f, which is less than the area under, all of the big M. And that ought to be perfectly believable just by looking at it, right? I mean, just because of the fact that little m was defined to be the minimum means that the area under the curve is going to be, kind of take on the constant function of the smallest value. I don't know what else there is to say. It should be very clear that the relationship between the areas holds. But you're being asked to use part A to show this a little bit more rigorously. And excuse me. And the idea is that, okay, so you're being asked to show that f is less than or equal to m is less than or equal to f average is less than or equal to m, big M. And to do that, you can just cite part A, right? You can just treat m of x as a constant function equal to little m all the time, and big M of x is equal to constant function big M all the time, and then just apply part A, and it should fall right out. Okay. So for the next one, if I is equal to something like root 2 x cubed e to the x squared dx. So one of the hard things about this problem is that this is a Gaussian integral, or at least e to the x squared is sort of the Gaussian part. So one of the ideas that might come to mind is applying integration by parts repeatedly until you get rid of this term, leaving you with just e to the x squared. But it turns out that that's actually pretty hard. So there's going to be a slight trick to this problem. And the trick is, what if we just rewrite this as x squared e to the x squared dx, right? It's a slightly inspired trick, but the idea is just to break down x cubed into two parts that are easier to deal with. And you see now that this is a perfect candidate for u substitution, because if we just let u is equal to x squared, then du becomes 2x dx. So this just becomes a u, this becomes a u, and then the x and the dx become your du. Pretty good, right? Pretty good. Don't forget the factor of 2 to account for the factor of 2, by the way. You just gotta divide through by that. But yeah, I'll let you take care of the rest. This should be a pretty straightforward u sub. Okay. So 4 is basically saying, all right, for A is asking you to do integration by parts, and there's not too much I can do here without just doing the calculation, right? But it's just saying use integration by parts twice. Use it to start with on u is equal to x squared, so then du becomes 2x dx. And then dv is equal to cos x, so v just becomes sin x. And you can see that if you do, right, this turns into uv, so then this, whatever this integral down here turns into x squared sine of x, because that's just u times v. And then you have to minus the integral of v du, so that's 2x sine x dx. And the idea here is just to continue the calculation using integration by parts again, with this being the u and this being the dv, and everything should fall right out nicely. So the next part is asking about a slightly trickier question, right? It's asking about the integral of something that looks like e to the x cosine of x. The problem itself has like an extra pi term or some factor in there, but it doesn't matter too much. It's just a constant that gets chain ruled. But the idea behind this kind of problem is that if you integrate it once, you kind of end up with this term that looks like So I'm going to do some integration by parts in my head, right? It's going to look like some uv. So let's call this integral I. Then I is going to be equal to some like uv minus the integral of, I think, e to the x sine of x. Is it plus or is it? I think it's actually plus. So this is after one integration by parts. So I'm going to say integration by parts. And then after two of these, the idea is after doing integration by parts once, the issue is that it doesn't really look any simpler, right? Here it was e to the x cosine of x, now it's e to the x sine x. But it doesn't really feel like we've made any progress. But rest assured that there is going to be a trick in here. And the idea is that if you do integration by parts again, you're going to end up with a minus e to the x cosine x, something that looks roughly like this, with a bunch of other stuff that's already integrated. And the idea is that if this is equal to I, you just have to recognize that this itself is also I. So what you just do is you just add I to the other side and then isolate for I. It's perfectly reasonable because this stuff over here is already solved, already integrated. And the idea behind this integration trick is essentially e to the x cosine x was really hard to integrate directly. So instead of integrating it directly, just move it to the other side and solve for I in this sort of roundabout way. It's a very good way to avoid actually having to do the hard calculation. One of our friends, our German friend, Yuli, actually has a name for this kind of integration. In the US school system, I never heard a name for this, so I kept on forgetting this trick. But the Germans apparently have a nice name where they call this Phoenix integrals. The idea is that if you're trying to integrate this original function, after some number of steps in integration by parts, you end up with the same function, maybe a slightly smaller one with like a 1 over pi or some constant in front. But the idea is basically that you sort of find the original integral rising from the ashes of the process of integration by parts. And I thought it was a very cute name, and it definitely helped me remember this trick better. But the idea here is, once you can get to this part where this is just nice, easy stuff, and then you have I and I, you can just solve for I, rather than having to integrate it directly. And it's very nice. It's very nice. Alrighty. Yeah. So then I basically don't have anything else to say for that other than just go through, do the trick, and keep your calculations. Make sure to check your calculations that you're not forgetting any constants from that pop out from the chain rule. But okay. The next one is the water level of a restricted tidal basin. It's modeled by h of t is equal to sine squared t plus 1/2. Okay. So we're being asked to consider two other functions. G of t is equal to 1/2 cosine. And I guess this is f of t is equal to cosine cubed sine plus 1. And what this question asks us to do is to start by integrating 1 over 2 pi, 0 to 2 pi, sine squared of t plus 1/2 dt. So this basically takes the average. This is basically equal to the h average over this interval. And looking at this, this is just a slightly tricky integral, excuse me. The 1 over half is easy, right? You can just integrate 1 over half, 1 over 2. But the sine squared takes just a tiny bit of massaging to get into something we know how to do, right? You wish we could kind of use u substitution. Let's say u is equal to like sine, but then du is equal to cosine of t dt. And unfortunately, I don't really see a cosine here, so this doesn't quite work. But what we do have access to, if you play around with the ideas a little bit, is a trig identity. Because we have that, remember from basic, remember from high school that cosine of 2x is equal to cosine squared minus sine squared of x. And cosine squared is just equal to 1 minus sine squared as well. So this is just equal to 1 minus 2 sine squared of x. And oh, look at that, sine squared, sine squared. We're kind of seeing a way to rewrite sine squared in terms of cosine 2x what does this turn into? This turns into 1 minus cosine 2x over 2 is equal to sine squared. And whereas sine squared is hard to integrate directly, everything here is actually reasonably easy, right? Cosine 2x is integrated basically the same as cosine of x. You just have to apply the chain rule to the 2. So basically do the substitution for sine squared, and voila, the integral becomes perfectly reasonable from there on out. Okay? So then, what's next? What's next? The next part asks you to do some sort of correction function to the original function over one tidal cycle. All right. So at this point, you have to sort of add these things together. Ourselves, what was g of t? Ah, right, this is cosine of 2t. I don't really think there's much to say here. I think, in fact, something just kind of cancels out, right? If this is 1/2 cosine 2t, and this is 1/2 minus cosine, well, 2x becomes a 2t over 2, I'm pretty sure the cosine part is just going to cancel out, leaving you with something really, really nice. But even if not, even if that cancellation doesn't quite happen, everything here should be something pretty reasonable to integrate. So I would advise you just to go through the work yourself and make sure you understand how basic integrals are done. All right. So then the next part asks you to do a slightly trickier integral with f being multiplied by h. So if f looks like cosine cubed of t, sine of t plus 1, and you're multiplying that by sine squared plus 1/2. Well, okay. We can FOIL this out a little bit, and you're going to get some terms that are easy and some terms that are quite nasty. So just FOIL. And what this looks to me is, I'm going to ignore the constants, but well, I'll write them here. Just make sure you're careful about them, right? Not to drop anything. But this looks like it turns into a cosine cubed t, sine cubed t, plus cosine cubed t, sine of t, over 2, plus sine squared of t, plus 1/2 dt. So from problem 1, we already knew how to integrate sine squared t plus 1/2. That should be easy enough. As for this part, this looks like a perfectly reasonable candidate for a chain rule, right? If you let u be equal to cosine then of t, then du becomes just equal to minus sine of t, dt. So apart from the negative sign, this is pretty much a perfect fit, because you have a sine t that gets multiplied by a dt. So this term right here should be perfectly reasonable to integrate just using a single trick. But this term is just a little bit nastier. Just a little bit nastier. And I think the idea here is that, well, we could either use the double... No. In fact, this identity doesn't really work because it's only good for sort of even powers, whereas here we're dealing with odd powers. But what we can try out instead, maybe, is just using sine squared of x is equal to 1 minus cosine squared. And then if we rewrite sine cubed as just sine squared of t times sine of t, and just apply this identity to the sine squared, what we get is instead the cosine cubed of t times 1 minus cosine squared of t times the sine of t. And once we distribute this out, we sort of get the cosine cubed minus cosine to the 5th times sine of t. And at this point, we can recognize that, oh, wait a minute, this is exactly what we had over here, right? If we just use the u sub of cosine t and du is equal to minus sine t dt, that integrates both the cosine cubed and the cosine to the 5th perfectly nicely. So the sort of spirit of this problem is that you just got to figure out a way to take something that you're not quite sure what to do with and massage that into something you do know, right? Into something like this that can be solved with a basic u substitution. That's the idea. That's all there is to say. All right. So for the next one, we're talking about a circle with radius 2. Y squared is equal to 4. And we're interested in just a piece of this circle that lies above the line y is equal to 1. So we can calculate this integral two ways, one using calculus and the other way using just regular old geometry. And the idea of the problem is to ensure that these two things are exactly the same. So let's figure out how to rewrite this area in terms of calculus, right? So the top function right here basically is y is equal to the positive square root of 4 minus x squared, right? If this was a negative sign, then this would be the bottom, but this is the square root with a positive sign is the top. Okay, so the idea is basically we want to integrate under, so how do I put it? We basically want to integrate the top of the circle and subtract out the y is equal to 1 line. And we have to figure out what bounds they are. But once we have that, this problem becomes, I think, perfectly reasonable. And okay, yeah, this isn't so bad, right? We just got to figure out what exactly this x value right here is. And we can do that using a tiny, tiny bit of trig. So if we're told that y is equal to 1 here, and we also know that the radius of the circle is 2, this is basically saying, okay, if this is 1 and this is 2, then this becomes root 3, right? So x becomes root 3, I think. And by symmetry, this side over here is x is equal to minus root 3. So I think this integral is just saying going from negative root 3 to root 3 of 4 minus x squared minus 1 dx. And that's all there is to it, right? For a problem like this, you just got to remind yourself what exactly is happening. 4 minus x squared is basically this area up top. Or sorry, not this area, but this line up top. And then subtracting out the 1 means that you're taking the area between the top and the bottom, like that. And that's exactly the area that you want. Right, so 4 minus x squared is the top, it's the arc. Minus 1 is the bottom, that's sort of like the floor. And subtracting out the 2 gives the area desired. Okay, so let's integrate this for yourself. Is there anything to say about this? This one is just a little bit tricky, because it, gosh, do you guys know how to integrate 4 minus x squared? I think this requires a tiny bit of a trig integral, right? Yeah, I don't think it's the most complicated thing in the world, but you should look up in your textbook how exactly to integrate a trig integral. Because there's not a very clear u du pair in this particular problem. So instead, what you're going to want to do, I think, is try to use the identity. What does this become? Right, 4 minus x squared sort of becomes 2 of 1 minus x over 4 squared. And the idea is this looks a lot like 1 minus cosine squared of, let's call it u. So if you just let cosine of u is equal to x over 4, so that cosine squared is equal to, excuse me, x over 2, x over 4. Why am I just messing this all up today? Right, so if you do this kind of u sub, I'm pretty sure everything will work out nicely, because then 1 minus cosine squared of u just turns into a sine squared. And then the square root of a sine, because the square root of the sine squared is just going to give you a nice sine, and that's going to make everything work out nicely. That's the idea. Alrighty. Okay, so then part B is basically saying do the, yeah, so, you know, I can't do all the work for you, right? So for part A, I would advise you to just go through the process of taking the trig sub. This should be a very standard integral in one of the chapters in your book. It's just a bit kind of tricky the first time you do it. But this is ultimately a very standard integral, this 4 minus x squared. So I would advise you to take a look at your text. Take a look at your textbook. Okay. So for part B, it's basically asking you to do the exact same thing, just without calculus, right? So the way I suggest this is do the area of the hemisphere, right? That's easy to find. That's just pi r squared over 2. is equal to this minus, okay, you can probably figure out what the area of this triangle is. Yeah, because it's just got radius 2 and height 1. Okay, that's very easy. Just use base height over 2, right? And then what else do you need to subtract? And then you need to subtract 2 of this like little wedge thing. Yeah. And remember that the area of this thing is just equal to, I think r theta, right? Where, wait a minute, is that even true? Hold on, how do you calculate area of this wedge? Am I going crazy? Okay, one way to do it is just take pi r squared, and then the whatever this angle is, let's say in radians, right? So then angle divided by the total angle, which is just 2 pi, right? So whatever theta is in radians, and divide that by 2 pi, and this should give you this area that's represented by this pi, and that should make perfectly good sense, right? Because if this is the area of the whole circle, then you just multiply this by whatever the fraction of this wedge is, and that fraction is going to be given by theta over 2 pi. And then just multiply that by 2 to represent the fact that there are 2 of these wedges, and you should be golden. All right, so for the very last one, we're talking about a forest that is home to 1,000 bunnies initially, but due to whatever environmental stuff, the population changes, and the idea is we've got some graph that looks kind of like this. So this is the death, I guess with respect to time dt, and this is the birth, bt. So without giving, the first part away, let's maybe use an analogy to economics. Let's say that one of these lines was, let's say I was running a business, and one of these lines was profit. Okay, so this is just my own analogy. If one of these lines was, I guess, if one of these rates was income per day, so what do I call this? Revenue per day. And the x-axis time. And then there was some other value, costs per day. Well, the integral of the difference would just be my total net profit or net loss, right? The integral of revenue minus cost is just equal to total profit or loss. So the same idea should be applicable to the rabbit population. You should be able to come up with an analogous explanation of what the integral of birth minus death rate ought to be. So the other thing that it's being asked is, after 10 years, will the population be greater than or less than the initial population? So one of the things to keep in mind is 10 years is only a portion of this graph, because I think it's over 40 years. And what it's asking you is basically, over this period, is the birth rate higher or is the death rate higher? And that should inform your answer as to whether or not the population is going to be increased or decreased over this period. So work that out for yourself. Now, it's asking if there is a time t greater than 0 at which the population will again be the same size as the initial. Okay. Well, that's basically saying, all right, so from part B, I'm not going to tell you the answer, but there's clearly going to be a net change because one of these is higher than the others. But the idea is, if this is kind of like negative, if this is like negative area, it's basically asking you on the other side, how much, basically how far do you have to go out in order for this to be an area of sort of the same size but different sign? And I say different sign because one of these, this curve was smaller than the other, but now it's greater, which is sort of saying whatever the birth or death rates, the net change gets reversed once you, how should I word this? If one of the sides is net negative, the other is net positive. So the idea is that when these two areas are equal, it's going to cancel out to be 0. That's the idea. So the question is just very roughly asking you to find the value of t such that this area is roughly equal to this area. That's all. All right. So then the final part is asking, suppose you know the average birth rate over 40 years is 100 bunnies a year, and the average death rate is 110. So B average is equal to 100, and D average is equal to 110. How many bunnies are there in the population at t is equal to 40? Well, all right. So remember that this integral is basically equal to b of t times 1 over 40. And this one is just equal to 1 over 40 times d of t. So that's from time 0 to 40, 0 to 40. And the idea is, well, okay, if you know the average, then you can just multiply this 40 to the other side to solve for the integral itself, b of t. And similarly, you can solve for the integral d of t. And to finish this off, we just got to go back to the original problem, right? The original problem asks you, how many bunnies are there in the population? Well, okay, at this point, you just have to plug what you know into the integral of b of t minus d of t from 0 to 40. So once you've isolated the value out for these integrals, you plug it right in, right? Because remember that the integral of a difference is equal to the difference of the integrals, because you have linearity. And what this tells you is, once you have a specific value, like a genuine number for this tells you the net change in population over whatever time. I guess over 40 years. Yeah, and remember that this is net change, so you also have to incorporate in the fact that there were 1,000 bunnies to start with in order to be able to tell what the population at the end is. But yeah, that's basically all there is to this one. It's a pretty simple set, and I think that'll be the end.